In your last two videos from Kahn on when he introduced the concept of derivatives, as you see up here, he derived where we define the derivative using a limiting operation. So he drew a secant line on a function of y equal x squared, and he showed you how you could use a limiting operation to calculate, what was the derivative of this function at x equal to 3. And in doing that, what have we found? What does the derivative at 3 really mean? Well, it means the slope of that tangent line right there. Okay. One thing I would like to do to add to that is kind of give a little motivation. Why are we interested in such things, and what's a kind of a common application of calculating that, what we might refer to as instantaneous slope. And down below here, I've drawn out a function. Now I've got a different function. I call it s of t. It's a function of time, and I call it its displacement. And this could be a model of me perhaps driving from Columbus. So at Columbus, I'm right here, and then over time I'm driving to Cincinnati. And this models how far am I away, or what's my displacement from Columbus. And you see, as I drive, what does that slope of this line mean? So we'll start off first of all talking about maybe let's draw in a secant line right here, and I could draw in a secant line. Draw in this, I could try the slope of this from, say, time equal to 0. Let's say, we're going to say time equal to 2 hours. We'll call this miles, and we'll put time in hours. Okay. And what does that mean? Well, I could take s of 2 minus s of 0 times 0. That would be what? That's the change in the displacement over the change in time, which would be 2 minus 0, which I would just call that the change in time. And if I look at the change in displacement over the change in time, that's what I'm going to define as a velocity. Look at what are the units of this thing in? Well, the change in s is going to be miles. The units are going to be in miles. Change in time is going to be hour. Hey, that looks like a velocity, and it is, okay? So this, we might refer to this as being an average velocity. Average velocity. So if I drove to Cincinnati, and this was, say, Cincinnati is 120 miles, so s of 2 is 120, so this is what? Let's put this in here, 120, and this is, I'll go from 0 to 0. And if I calculated this, you'd find out my change in s is 120 miles, my change in t is 2 hours, my average velocity, that there would have been what? Well, it's going to be 60 miles per hour. Notice I am not speeding when I drive to Cincinnati, maintaining a good, safe speed. Now, that's a secant line. Well, what if we could draw secant lines between different points as Kahn did in his video, but if we take a limiting operation and say we want to find out, well, let's go to that point there, and let's call that, let's just say that's a 1 hour, at 1 hour there. Okay, at 1 hour, if I wanted to draw, what would this mean, the slope? The slope of the tangent line right at 1 hour, well, I would call that the following. That would be, I might call that velocity. I would call that velocity at 1 hour, and I could call that what? The derivative. The derivative of the displacement function at 1, defined to be the same thing, notice, and that would be what? I could write it as a limiting function, and I'd say what? Well, let's let h go to 0 again, and what do we want to? We want to do s of 1 hour plus h minus s of 1 hour, right? Again, that's just the numerator here is just the change in displacement. And then over here, we're going to have, well, what's the change in time? It's going to be 1 plus h minus 1. And again, that's nothing more than the limit as h goes to 0 of the change in s over the change in time. Okay, and if we found that out, if we found this thing, we would get the slope. What does that mean? Well, that's going to be, we would refer to that as my instantaneous velocity. Instantaneous, there's another taneous in here, okay? Instantaneous, okay? Velocity at this point. Now, we make a distinction between velocity and speed because velocity could go negative. I could turn around and my velocity could be negative 10 miles per hour. But in this particular example, notice everything's always increasing. I'm going to Cincinnati. I haven't turned around. So speed and velocity are the same. So this instantaneous velocity is going to be the same thing your speedometer is going to tell you while you're driving. And now you can see, we can do a little story behind this. See, right here we start off at Cincinnati, and you start off, you know, you're not moving. Then you go a little faster, right? The slope gets higher, and it looks like about right here I almost get on that maximum speed. In fact, the question is, have I crossed the speed limit at that point? I don't know. We'd have to see. We'd have to calculate that slope to know. But then I'm starting to slow down, and you see here, looks like I hit a little bit of a traffic jam, you know, right in between, about halfway in between Columbus and Cincinnati. And then I start speeding up again, right? Because what's the slope of this tangent line? The slope of this is instantaneous velocity. And in this case, that's what my speedometer would say. Then I speed up a little more, and as I pull into Cincinnati, of course, you would hope I stop, and I do. Right here, the slope of this tangent line is what? The slope here is 0, so my car is not moving. So notice what calculus was allowing us to do here. We could calculate the average velocity. The average velocity was just how far did I go in 2 hours? It was s of 2, this point here, minus s of 0, divided by the amount of time, okay? Kind of a coarse estimate of my speed. But if I really wanted to zoom in on the function and find instantaneous velocity, or in this case, that would be what my speedometer's reading, I would have to find the derivative, or the instantaneous slope of this function. And again, calculus with the limiting process, that's why we study limits. So we could actually let the denominator of this averaging function go to 0. You will see in your homework tonight that you'll be asked to find a tangent line at a function, of a function at a particular point. And we'll go back to the Kahn example here and show you how to find that as we kind of fill in a few things here. But we notice at this point 3, we found out in the video that with the limiting process, you could calculate that the derivative at 3 was equal to 6. Okay, what did that derivative mean? That derivative actually turns out the slope of this line, the tangent line, is in green here. The slope of that line, well, is equal to 6. Well, how do we turn that into a tangent line? Well, let's go back to our point slope definition of a line. Okay, in order to define a line, we need a slope. Well, we have a slope here. We also need a point. Do we have a point on this line? Well, we do have a point on the tangent line. We know that at the point of tangency, the tangent line shares a point with the function itself. So there's a function here, 3. x3 is on there, and 9. We know this point, 3, 9, is also on the line. So if we look for a point slope definition of this, we'd say, well, the slope would be, we might write that down like this. The slope is equal to y minus the y value that you know over x minus the x value that we know. And in general, then, multiply this by, multiply both sides by what? X minus x of 0. X minus x of 0. What is x0, y0? That is 3, 9. What is the slope? Slope is 6. So maybe I should have put this over here. x0, y0. y0 meaning that's the point I know. And these cancel here, and I get, well, y minus y0 is equal to m times x minus x0. And I wouldn't simplify your line any more than that. Okay, you can multiply things out, but you could leave your answer kind of in this form. So in this case, it's going to be what? Well, it's, if I did this, I'd do something like, I'll start back up here, and I'd say 6 is equal to y minus 9 over x minus 3. And I'd say, well, y minus 9 is equal to the slope 6 times x minus 3. And I would leave my answer at that, like that. There's really no need to do this. Y equals, okay, 9. I know we can do this. 6x minus 18 equal to, what, 6x minus 9. That's also correct, of course. But again, just to make this quick and easy, you could stop right here. This is the equation of tangent line.